Good morning. My name is Bartosz.Stojewski, and I'll have a presentation called Implementation of Relaxation Method in Solutions of Ginzburg-Landau Equation. I'll try to explain Ginzburg-Landau theory, what is a relaxation method, and how to use it in solving the Ginzburg-Landau equation. I also describe few minor problems that will be required to understand it. Here is the plan of the presentation. First, I'll explain what is a differential equation and a harmonic oscillator. Then in the second part, I'll try to describe numerical schemes for first and second derivative and how to calculate them by using a number of environmental points. In the third part, I'll describe Ginzburg-Landau equation and what is exactly a superconductor. Fourth part will be describing what is a relaxation method and how to use it in solving various problems, Ginzburg-Landau equation included. Fifth part will be code parallelization with a few examples of use. I will describe few directives in OpenMP and how to use them. To start with, I need to explain what is a differential equation and how to use it in real life. An equation that contains the derivative of an unknown function is called a differential equation. The rate of change of a function at a point is defined by the derivatives of the function. Such equation relates these derivatives with the other functions. Differential equations are mainly used in the fields of biology, physics, engineering, and many other. The main purpose of the differential equation is for studying the solutions that satisfy the equations and the properties of the solutions. Let's discuss the definition, types, methods to solve the differential equation, order, and the degree of the differential equation. A differential equation is an equation that contains at least one derivative of an unknown function, either an ordinary derivative or a partial derivative. Suppose the rate of the change of the function y with respect to x is inversely proportional to I. On the slide, you could see various examples of differential equations. The order of differential equation is the highest order of the derivative appearing in the equation. In shown differential equation examples, the highest derivative are the first, the third, and the fourth. And this is how we determine order of the differential equation. First one is 1, second one is third, and fourth one is 4. If a differential equation is expressible in a polynomial form, then the integral power of the highest order derivative that appears in called degree of the differential equation. The degree of the differential equation is the power of the highest order derivative present in the equation. To find the degree of the differential equation, we need to have a positive integer as an index of the derivative. In the shown example, the order of the differential equation is 4, and the degree is 3. If the differential equation is not accessible in terms of a polynomial equation having the highest order derivative as the leading term, then the degree of the differential equation is not defined. And now I'll talk about types of the differential equation. You can see the how we classify them here on the slide, and I will describe the differences between them. First, the ordinary differential equation, also known as ODE, is an equation that contains only one independent variable and one or more of its derivatives with respect to the variable. Thus, the ordinary differential equation is represented as the relation having one independent variable x, the real dependent variable y, with some of its derivatives with respect to x. The ordinary differential equation can be homogeneous or non-homogeneous. A differential equation in which degree of all terms is the same is known as the homogeneous differential equation. In general, they can be represented as shown in the example. The shown example is a homogeneous differential equation of degree 4. A differential equation in which the degree of all the terms is not the same is known as a non-homogeneous differential equation. Example shown below. On the right, we have an equation involving only partial derivatives of one or more functions.
Excuse me, is there a misprint? There's supposed to be the second variable should be y, right?
Yes. Sorry, my mistake. Ordinary differential equations applications in real life are used to calculate the movement or flow of electricity, motion of an object to and from like a pendulum, to explain thermodynamic concepts. Also, in magical terms, they are used to check the growth of diseases in graphical representation. Differential equations are useful in describing mathematical models involving population growth or radioactive decay. One of the real-life usage I'll describe is a harmonic oscillator. A harmonic oscillator is a system that, when thrown out of equilibrium, is subjected to a force proportional to the deflection, trying to restore this equilibrium. This results in a motion limited in space and harmonically oscillating, that is, one in which the dependence of the deviation against time is a sine or cosine function. A simple example of a mechanical harmonic oscillator is a wave M suspended by a spring. Hooke's law says that the body of the deformed spring is subjected to a force directed against the direction of the deformation and proportional to the distance from the equilibrium state. The equation of motion for a mass suspended from a spring is simple if we ignore the force of gravity or place the system in weightless state. Only the restoring force of elasticity acts on it, so we can use the equation of mass m according to Newton's second law of motion. And this is called a simple harmonic oscillator. There is also a dampened harmonic oscillator, but I'll focus on the first one. By using Hooke's law, which says that the spring extended or compressed by some distance x scales linearly with respect to that distance, we can define the movement of simple harmonic oscillator as shown on the first image on the slide, where F is a restoring force, K is a constant related to spring, X is a distance to equilibrium position, and X is a versor of X with length of 1. From Newton's second law of motion, we know that force equals mass multiplied by acceleration. We also know that acceleration is the second derivative of the position r with respect to time in Cartesian coordinates, as shown on the third image. But in our case, we only have x coordinate, so that's why we only have first part of the acceleration, the y and z are equal to 0. By putting those two equations together, which is Newton's second law of motion and Hooke's law, we can get such differential equation that gives us information what kind of x from t function we need to look for if we want to find solution to the simple harmonic oscillator. We could notice that without dampening, the motion is periodic and is repeated in sinusoidal fashion. This is why we can try to find analytical solutions with sinus. On the left, we can see that the position is described as a sinus omega t. And the first derivative is actually our velocity. And the velocity is equal a omega cosinus omega t. Then we put those two equations to the equation shown here in the last line, and by solving that we can get that we can calculate omega, which is dependent on the constant k and the mass m. Then we can calculate initial position, which in this case is equal 0, and we can calculate starting velocity, which is shown here. But now what will happen if we try to look for analytical solution with a cosinus? This is how it looks like. If we calculate omega, we get the same solution as we get in the previous situation. If we calculate starting position and initial velocity, then we get that starting position is b, and the starting velocity is called 0. Those two situations correspond to the situations where first situation corresponds to that our harmonic oscillator is in its equilibrium point and it has some starting velocity. Second situation corresponds to the situation when we stretch the string to the point B and we let it go. That's why the starting velocity is 0. To obtain the general solution, these two solutions should be summed, and this is how it looks like. The starting position is b, and starting velocity is a multiplied by omega, a omega, and if we put that to our general equation, we get this equation shown on the right hand side, and this is one of the general solutions for a simple harmonic oscillator. Both sinus and cosinus have a period of 2p, so we can calculate t, and we can see how omega depends on our t. There is also other general solution for the simple harmonic oscillator, and it is shown right here. On the left hand side, we can say that A is amplitude showing the maximum deflection. Omega 0 is natural frequency of oscillator vibrations. psi is an initial phase of vibrations, defines the state of an oscillator at the beginning of vibrations. For example, when it equals 0, then x equals a sinus omega 0t. And if it equals 2p, then it equals a cosinus omega 0t. We can show that first general solution and second general solutions are the same if we use trigonometry rule shown on the right-hand side. Sinus alpha plus beta equals sinus alpha cosinus beta plus sinus beta cosinus alpha. And we can see that second general solution is equal to the first general solution. But what if we don't want analytical solutions, but numerical solutions? One of the most simple solutions is to use Euler method for harmonic oscillator. Here we have the differential equation of a simple harmonic oscillator as shown on the previous slides. We must split this into two coupled first order equations as shown below. By using Euler's method, we have we can prepare a computer program that will help us calculate numerical solutions for simple harmonic oscillator. In the program, we have K is a spring constant, M is mass in kilograms, xt is initial position, t0 is initial time, v0 is initial velocity, and dt is a time interval. This is one of the simplest methods of calculating, of solving the simple harmonic oscillator. That's why it has a large error. There are more precise methods, but I'll restrain myself to describing this one. And that concludes first part of my presentation. Now I'll go to the second one, which is representation of numerical schemes for the derivatives that take into account a number of environmental points. Computers are great tools for carrying out long, tedious, and complex calculations. However, they are not perfect. The n-body problem is one example of when computer algorithms needs to be optimized in an appropriate way. The problem is to simulate the interaction of any number of bodies in a multidimensional space, like single electrons in semiconductor nanowires. The problem is described by a non-linear partial equation, which makes them extremely difficult to solve with the analytical method. A possible solutions to this problem are numerical methods that replace computationally expensive operations with simple operations, such as addition or multiplication. Despite the current procedures for calculating numerical derivatives present in programs such as Mathematica or MATLAB, there are numerical schemes that allow us to get a solution with decent precision without needs for expensive operations. Numerical methods for ordinary differential equations are methods used to find numerical approximations to the solutions of ordinary differential equations. The numerical methods for solving first-order derivatives often fall into one of two large categories: linear multi-step methods or Runge-Kutta methods. In this presentation, I'll focus on the first group of the aforementioned methods. Approximating derivatives is a very important part of any numerical simulation, when it is no longer possible to analytically obtain a value for the derivative. For example, when trying to simulate a complicated ODE. It is of a much importance though, as getting it wrong can have detrimental effects on the solution. To get into that, let's start with the most basic forms of numerical methods. First, we need to know what's a finite difference. A finite difference is a mathematical expression of the form shown in the text here. The approximation of derivatives is by finite differences plays a central role in finite difference methods for the numerical solutions of differential equations, especially boundary value problems. In numerical analysis, finite differences are widely used for approximating derivatives, and the term finite difference is often used as an abbreviation of finite difference approximation of derivatives. Three basic types are commonly considered: forward, backward, and central finite differences. Forward difference are useful in solving ordinary differential equations by single-step predictor-corrector methods, such as Euler or Runge-Kutta methods. This forward method is shown on the image below. Backward difference are useful for approximating the derivatives if data in the future are not yet available. Moreover, data in the future may depend on the derivatives approximated from the data in the past, such as in control problems. And again, it is shown on the image below. If the data values are equally spaced, the central difference is an average of the forward and backward differences. It is clear that the central difference gives a much more accurate approximation of the derivative compared to the forward and backward differences. Central differences are useful in solving partial differential equations. If the data values are available in both the past and in the future, the numerical derivative should be approximated by the central difference. Previous formulas were correct only for the first derivative, and they were using 2 points in space. It's impossible to approximate second derivative with only 2 points in space. That's why we need to have at least 3 points for the second derivative. Those are the most simple formulas we have to approximate the value of the second derivative in backward, central, or forward method. But how do we even get such formulas? Are those mentioned the only one we can receive? No, the Taylor series expansion can be used to generate high accuracy formulas for derivatives by using linear algebra to combine the expansion around several points. In mathematics, the Taylor series of a function is an infinite sum of terms that are expressed in the terms of the function's derivatives at a single point. For most common functions, the function and the sum of its Taylor series are equal near this point. Taylor series allows us to expand the function into an infinite series. If the function is infinitely differentiable at number h, we can use the Taylor series to approximate the function. We can derive the backward, the forward, and the center divided difference method using Taylor series, which also give a quantitative estimate of the error in the approximation. Below, you can see how the Taylor series looks like. In order to determine the derivative of the function at a given point, use the knowledge about the compatibility of this function in its immediate vicinity. An approximation of the derivative can be obtained by expanding the function to the Taylor series and then by extracting the proper components from it. First, we determine for which points we derive the derivative. Their number is related to the accuracy of our solutions. The more precisely the approximate derivative. We chose the points next to the point where we want to differentiate. The postulated derivative of the second degree at the point is expressed by 5 points from the closest vicinity at the points. Now, here is shown how we expand the individual components by applying Taylor series to the fifth derivative. Then when we do that, we put the previous obtained expressions into our linear combination. And then we are then we obtain a system of 5 algebraic equations that allows for the determination of coefficients approximating the given second derivative of the function at the point x, as shown in the table on the right-hand side. And this is how it looks like finally. This is our final form of a 5-point method for second derivative. Sorry. Those was the example of how we get the method for second derivative by using 5 points, but there's nothing stopping us from doing it for more points. For example, like here, 11 points, being the vicinity of the point of which is made a double differentiation. And the process is looking exactly the same. By solving analytically or numerically the obtained system of the equations, we obtain the coefficients shown in this table. By using this method, we can get methods for approximating derivative in various situations, like multiple variables, functions, or mixed derivatives. The Taylor series allows us to obtain various methods for various differential equations. This concludes the second part of the presentation. Third part will be describing Ginzburg-Landau theory and what is a superconductor and how to solve a Ginzburg-Landau equation. Superconductivity is a set of physical properties observed in certain materials where electrical resistance vanishes and magnetic flux fields are expelled from the material. Any material exhibiting these properties is a superconductor. Unlike an ordinary metallic conductor whose resistance decreases gradually as its temperature is lowered, even down to the near absolute zero, a superconductor has a characteristic critical temperature below which the resistance drops abruptly to zero. An electric current, though a loop of superconducting wire, can persist indefinitely with no power source. A characteristic effect of the superconductors is pushing the magnetic field out of the material, called the Meissner effect. In the first type of superconductors, or the concentration of the magnetic field into vortices in the second type superconductors. We can classify superconductors in many ways. For example, due to its critical properties, we specify type 1 superconductors in which the superconducting state is destroyed at the specific critical magnetic field BC, or type 2 superconductors in which at the specific BC1 magnetic field, the magnetic field penetrates the superconductor and creates a mixed state. And above the BC2 field, the superconducting state is destroyed. Other classification is due to the transmission temperature, low temperature superconductors with superconductive transition temperature below the boiling point of liquid nitrogen, which is 77 and kelvins, and high temperature superconductors, which is with a superconductivity temperature above the boiling point of the liquid nitrogen. Those are not the only way to categorize superconductors, but for now it's enough. Now we proceed to the Ginzburg-Landau theory of superconductivity. In physics, a theory describing superconductivity like a phenomenon consisting in the almost complete disappearance of electrical resistance, which allows a a current of very high intensity to flow almost without losses. The magnetic field cannot penetrate the superconductor, which causes the object made of it to levitate over the magnet. The theory was proposed by Vitaly Ginzburg and Leigh Landau. The Ginzburg-Landau theory of superconductivity, like other theories of phase transitions, is phenomenological in nature, which means that it describes a phenomenon in the form of a certain equation without referring to its sources. It is created thanks to the skillful matching of mathematical dependencies, but it does not allow for understanding the phenomena occurring in the micro, which are the basis of superconductivity. Based on Landau's previously established theory of second-order phase transitions, Ginzburg and Landau argued that the free energy F of a superconductor near the superconducting transition can be expressed in terms of a complex order parameter field, where the quantity of psi in the power of 2 is a measure of local density of Cooper pairs, which are a pair of electrons or other fermions bound together at low temperatures in a central manner. In this equation, Fn stands for free energy during normal phase. Upside down triangle is a nabla operator. When applied to a field, a function defined on a multi-dimensional domain, it may denote any one of three operators, depending on the way it is applied: the gradient, or locally steepest slope of the scalar field, the divergence of the vector field, or the curl of the vector field. E is the charge of an electron, M is the effective mass, B is magnetic field, and A is a magnetic vector potential. A magnetic field B is a vector field that describes the magnetic influence on moving electric charges, electric currents, and magnetic materials. In classical electromagnetism, magnetic vector potential A is the vector quantity defined so that its curl is equal to the magnetic field. The curl of a field is formally defined as the circulation density at each point of the field. And
yeah, there's a small remark. Yeah, so you have only assumed the existence of AZ vector potential that is acceptable. I mean, the second Ginzburg-Landau equation that is specified. So this is what is shown is just one specific case, because in general we can have AX and AY and AZ components that is non-zero. Nevertheless, the equation that is shown here, Ginzburg-Landau equation, is formally correct. Okay.
I'm sorry, I'm describing the equation on the first image. I'll go to the second one.
Okay, sure. Go ahead.
Mm-hmm. There is an equation that B equals a nabla operator multiplied by magnetic vector potential. And on the second image, we see that if we minimize the free energy with respect to the variations in our vector potential and order parameter, we acquire one form of Ginzburg-Landau equation. And this is just one of its available forms. This is a two-dimensional Ginzburg-Landau equation we attempt to solve. It is impossible to numerically solve this equation by hand. For that, we need computers and proper methods to solve the Ginzburg-Landau theory. In this presentation, I'll describe two methods. First one, more simple, I'll describe in the next part of my presentation, which is relaxation method. Right now, I'll describe how we can solve the Ginzburg-Landau equation using a program called Svirl. Svirl is a GPU-accelerated solver of complex Ginzburg-Landau equations for superconductivity. It consists of time-dependent solver to describe vortex dynamics and free energy minimizer to accurately find static configurations. Its main features are 2D time-dependent Ginzburg-Landau solver, 2D Ginzburg-Landau free energy minimizer, finite and infinite Ginzburg-Landau parameters, and a few others features that are useful in this particular scenario. Here we can see a few examples of using this program. The screen on the left shows use case of user-defined geometry of superconductor, and the one on the right shows spiral variations in the linear coefficient. Another example is can demonstrate capabilities of building a plotter. Those were the examples provided by the creator of Svirl, and they show good capabilities for custom usage. If you know Python and you are interested in Ginzburg-Landau theory, then this might be a good starting point for you. Now we proceed to the fourth part of my presentations, which is the relaxation method of solving various problems. In numerical mathematics, relaxation methods are iterative methods for solving systems of equations, including nonlinear systems. Relaxation methods were developed for solving large, sparse linear systems, which arose as finite difference discretizations of differential equations. They are also used for the solution of linear equations for linear least squares problems, and also for systems of linear inequalities, such as those arising in linear programming. They have also been developed for solving nonlinear systems of equations. Relaxation methods are important, especially in the solutions of linear system used to model elliptic partial differential equations, such as Laplace's equation and its generalizations, Poisson's equations. These equations describe boundary value problems in which the solution functions values are specified on boundary of the domain. The problem is to compute a solution also on its interior. Relaxation methods are used to solve linear equations resulting from a discretization of a differential equation, for example, by finite differences. Iterative relaxation solutions is commonly dubbed smoothing because with certain equations, such as previously mentioned Laplace's equations, it resembles repeated application of a local smoothing filter to the solution vector. Interactive relaxation of solutions is common. One of the simplest of the relaxation methods is the Jacobi method. In a numerical linear algebra, the Jacobi method is an interactive algorithm for determining diagonal solutions of the dominant system of linear equations. However, I will not go into too much detail here. I just want to specify that Jacobi method is one of the simplest relaxation methods.
Excuse me, can you come to previous slide? Just yes. For the sake of comment. So you mean equation A matrix time X vector is equal to B, right? That's yep, the equation, yep. Right? All right. So you make an initial guess of X vector, that is a solution, and after this you make a next iteration, and the recipe for iteration is on the right side, right? That's yeah. Yes. All right. Yes. Sounds great. Okay. Thank you. Mm-hmm.
Yes. A relaxation method can be used to solve Ginzburg-Landau equations. At first, we consider the simple one-dimensional form of Ginzburg-Landau equation of the form on the left, where the gamma is some constant. Maxwell equations gives us the equation on the right, where G is the electric current density from Ginzburg-Landau theory. To apply a relaxation method to the equation, we need to follow certain steps. we must assume values of vector potential Ax and order parameter psi from X, as well as the points and values of certain variables. With them, we can calculate initial electric currency and gradients of Ax from X and psi from X. Then we iterate the above solution desired number of times. To summarize, it looks like the steps on the slide. This is if we proceed with such steps, desired amount of times, we get better and better solutions for our Ginzburg-Landau theory. After executing such method, despite that the initial values of psi were far from physical intuition and proper numerical solutions, after a bunch of iterations, we get a solution that corresponds to physical intuition. And those are steps for one-dimensional Ginzburg-Landau equation. Next example was solving two-dimensional Ginzburg-Landau equation, and as in the form shown below. At first, we consider the case of a zero magnetic field that implies that AZ is equal to 0, and one part of the equation will equal 0, the one with AZ in it. Relaxation method for Ginzburg-Landau equation in 2 dimensions is pretty similar to the algorithm we used for Ginzburg-Landau equation in 1 dimension. Alpha and beta are simulation parameters, and we try to assume AZ and psi from X and Y. Here are the description of the steps we should do to solve Ginzburg-Landau theory for 2-dimensional problem. Here's one of the examples of how we can solve Ginzburg-Landau theory in one situation. We continue the study on unconventional Josephson junction when we place the non-superconducting element on the top of the superconductor slab. This time, the non-superconductor strip is placed inside the superconductor. We also can consider placement of less superconducting bar on the more superconducting bar, a more negative alpha coefficient. Such structure is shown on the image below. This is our alpha field for solving Ginzburg-Landau equation. And here's the result of the simulation run on the given alpha field. The presence of the normal strip reduces superconducting order parameter, SCOP, in more significant way, as in the case of weakening of the superconductor, what is given in the slide. The diffusion of Cooper pair from the superconducting strip into superconducting strip takes place. In the case, in this case, we can see how our simulation shows possible physical solution for the equation. Then I can show my program for this is another example of solving Ginzburg-Landau theory. On the left, we can see initial distributions of alpha, and the dark blue space is a superconductor, light blue is a vacuum, and yellow is a non-superconducting material. On the right, we have initial distributions of superconducting order parameter. This is basically our guess. We are trying to guess the initial distribution. It can look differently. Then we can, after running a simulation, we can see that it looks like that, and we can see that both that average free energy and average error are exponentially lowering with each step of the iteration. That means that we get more precise solution. Here is another example. Our initial distribution of SCOP is the same as in the previous situation, but we have different distribution of alpha field. And this is how it looks like when we run the simulation. And that concludes the fourth part of my presentation. Now we continue to the last part, which is code parallelization. Usually, when we run programs on our computer, then it uses only one thread, which causes long running times. Parallel programming helps reduce those times drastically. Complex problems require complex solutions. Instead of waiting hours for a program to finish running, why not utilize parallel programming? It helps developers break down the task that the program must complete into smaller segments of work that can be done in parallel. While parallel programming can be a more time-intensive effort upfront from developers to create efficient parallel algorithms and code, it overall saves time by leveraging parallel processing power by running the program across multiple compute nodes and CPU cores at the same time. Parallel programming works by assigning tasks to different nodes or cores. In high-performance computing systems, a node is a self-contained unit of a computer system, contains memory and processors running on operating system. Processors, such as central processing units, CPUs, and graphic processing units, GPUs, are chips that contain a set of cores. Cores are the units executing commands. There can be multiple cores in the processor and multiple processors in a node. With parallel programming, a developer writes codes with specialized software to make it easy for them to run their program across on multiple nodes or processors. One of the ways to include parallel programming is in our applications is to use OpenMP, which is Open Multiprocessing, an applications programming interface for writing parallel applications for multiprocessor computers with shared memory. Important thing about OpenMP are real and virtual threads. We will distinguish between real threads and virtual threads by equate real threads with available cores or processors. Virtual threads are threads that are manually created by the program for its needs. For multi-core processors, the optimal situation is that each and every virtual thread is served by one core. If we have a single core processor and we create, for example, 4 threads, and if we perform a given task on these threads, we will not get any accelerations of calculations because these virtual threads are actually handled sequentially by one processor when one of them is running. The OpenMP API is composed of 3 distinct components: compiler directives, runtime library, routines, and environmental variables. Compiler directives type in your source code are instructions for the compiler on how to parallelize your code. If you set the right flags on the compilation, these directives are read and understood, else they are ignored. Runtime library routines typed in your source codes are the function calls to functions of the OpenMP library, omp.h in C or C++. And an environmental variable are handled in the terminal. This is a variable used by the system that can be modified or retrieved. Most of the constructs in OpenMP are compiler directives. The general rule how to use them is showed here on the slide. Before we can use OpenMP directives, we need to include following line in our codes. This is actual C or C++. In the header, we must first include our omp.h header, which allows us to use OpenMP directives. And then in the function code, we need to set our threads to a thread number, which is usually the number of our processors in our computer. The word OMP is an OpenMP keyword. Develop use the parallel directive to tell the compiler the area of code to be paralleled. Another directive, for, tells the compiler that for loops will be paralleled. Then it is determined which variables used in the loop will be shared and which will be private. Common variables are available for each thread, but only one specific thread has access to a given private variable. In the example program here, the private variables is I, the loop counter. By making them private variables, each thread has its own internal iteration count. For example, if a loop is 100 in length, then by splitting it into 4 threads, each will have 25 iterations to execute. And the private variable will tell it where the computation is running. Strictly speaking, each thread gets a copy of the variable I and works on that copy. This is a very important part of the program, and the user must correctly determine which variable is to be shared and which is private. Note that we do not have to specify how many threads the program should use. OpenMP itself detects the number of threads available and allocates each approximate number of iterations to be performed. For example, if there are 100 iterations to execute and the program has 2 threads available, the first 50 iterations will be executed by thread 1 and the remaining 50 iterations by thread 2. It should be noted that not always iterations are distributed evenly between threads. It should be remembered that the difference between the program execution time on a multi-core computer and the execution time of the same program on a single computer will be noticeable only for time-consuming operations. In practice, this usually means a large number of iterations or the need to perform a complex function during each loop run. The above program has an outer loop, the purpose of which is to emphasize the time difference between the parallel and sequential execution of calculations. Here we have some useful directives that we use in our OpenMP code. The default directive gives variables used in the loop default attributes to determine whether they are private or undefined. In C or C++, there are 2 ways to use this command: default shared or default none. In the first example, we declare that all variables are shared, and the second one, we say that the variables are undefined, which means we need to define which are shared and which are private. The difference schedule is used to its use is limited only for the loops for. If used in a different context, it will result in an error signaled by the compiler. With this directive, we can have some extent control how the iteration is distributed among the available threads. Static means that tasks are distributed equally to the threads by the chunk size where we input it in the second attribute. Dynamic means each thread is assigned the number of iterations specified by the chunk parameter. Guided means the iterations are split between threads similar to the dynamic options, with the difference that the size of the assigned subset of iterations decreases over time. Runtime means that chunk value is based on OMP schedule environmental variable. Reduction means that we inform the compiler that we will perform operations, successively calculated values of other variable to a variable. The compiler will make the appropriate number of private copies of the variable for each thread and split the iterations between the available threads. In OpenMP, at the end of each code block, distinguished by the directive parallel, there is so-called barrier. A thread, when thread encounters the barrier, the set thread will wait for other threads to finish their tasks. And the programmer can manually put the barrier in a certain point of the code by inserting the directive mentioned here, pragma OMP barrier. No wait clause actually deletes the barrier at the end of the default barrier at the end of chunk of code, which I mentioned by when describing the pragma OMP barrier. And those were useful directives that are most commonly seen in OpenMP code. I attempt to write a program that allows user to calculate the Ginzburg-Landau theory for various inputs. I also try to convert it on C++ and use parallel programming with it. I'm using OpenMP, and here is a little fragment of my code. You can see that this is basically a calculation of an initial SCOP field, assigning values to the alpha field and calculating the initial AZ field. Throughout the program, I mostly used pragma OMP parallel 4 with an additional collapse clause. It tells us how many loops in a nested loop should be collapsed into one large iteration space and divided according to the schedule clause. The sequential execution of the iterations in all associated loops determines the order of the iterations in the collapsed iteration time. And here you could see the final distribution of superconducting order parameter. On the left, there is a simulation run in MATLAB, and on the right, there is a simulation run in my C++ parallel program. It still needs some work, but you could see that estimated running time is drastically reduced. And that was the goal of using OpenMP. And by polishing the code, I hope to get the same solutions, but with using the same parameters, but with much less time. Here is another example. The one on the right looks more well, it needs work, yes, as I mentioned before. But as you could see, there is also a huge reduction of running time. And that concludes my presentation. Thank you for your attention.